Welcome back as we begin Chapter 12 of Pre-Calculus Made Difficult, where our first order of business will be to introduce radians. Everybody knows that we can measure the size of an angle in degrees, but we can also measure the size of an angle in radians. A radian is just another unit of angle measurement, just like you can measure a length in, say, inches or centimeters. And of course, there's a simple conversion between inches and centimeters, and there's an equally simple conversion between degrees and radians that we will soon figure out. And the first eminently reasonable question someone should ask when they hear about the existence of this alternative angle measure, radians, is, well, who needs it? What's the point of having a second way to measure the sizes of angles? I mean, we understand roughly why we have inches versus centimeters. The inch is just some very arbitrary measure that was introduced long ago in England, I presume, where there are 12 inches in a foot and 5,280 feet in a mile, and it's all part of a bizarre system of measurements, many of which are unknown even to people like me who grow up in one of the few remaining countries that uses such a system. But of course, the parts that you do know and you get an intuitive feel for, well, they stay with you. And to be honest, to me, at a gut level, the metric system still feels like witchcraft. But of course it isn't. At an intellectual level, I understand, and everybody understands, the metric system was designed to bring some order to all the crazy measurements in the old British system. A meter contains how many centimeters? 100, of course, it's right there in the name. A kilometer contains how many meters? Again, it's right there in the name, 1,000. It's a much more sensible system. Easy to learn, easy to understand. But even there is still something arbitrary about the metric system. Yes, sure, everything comes in nice packages of 10 and 100 and 1,000 and so forth. But what's so wonderful about powers of 10? I mean, sure, maybe it's nice to just have powers of something, but why 10? Well, that seems to be basically just an accident of human biology, and the fact that we have 10 fingers, which makes 10 a fairly natural-seeming base. But there's nothing intrinsically special about it. If we had evolved with, say, 12 fingers, some ingenious person would have eventually proposed a system of measurements where everything was chopped up into packets of 12 and 144 and whatever 12 cubed is, 1,728, as it turns out. And as far as our day-to-day activities go, that's fine. We don't mind the arbitrariness of having base 10 in our system. But in mathematics proper, we would like, where possible, to use units of measurement that are somehow intrinsic to mathematics itself and don't depend on the language we're using or the culture we come from or even the species to which we belong. Well, if we are measuring lengths, we have no choice but to introduce a totally arbitrary unit. We'll have to pick some particular measurement, call it 1 unit, and then we can define other units in terms of that. But that unit is necessarily going to be somewhat arbitrary in the sense that it is not part of mathematical reality. It's something we're laying on top of mathematics. Such is the state of affairs if we're talking about a unit of length. However, if we are talking about a unit that measures the size of an angle, we do have something built in that is not at all arbitrary. That is part of mathematical bedrock. So we can define a sort of intrinsic unit of angle measurement. And that is how we are going to come up with radians. But before we get to radians, let's dwell for a minute on degrees. Even when we're talking about degrees, we get a hint of how measuring angles is a different kind of proposition than measuring lengths. We get a hint that there's some intrinsic aspect to it. Because what is a degree? If you had to define a degree, how would you define it? Well, you'd probably do something like this. 1 degree is defined as 1/360th of a full rotation. Well, that's kind of an interesting idea. What's interesting about it is that it involves something that is part of fundamental mathematics, this notion of a full rotation, which of course is tied to the idea of a circle. We're doing a complete rotation around a point. So that piece really is built into mathematics. But then this rough definition of a degree also contains something that seems totally arbitrary. 1/360th. Why in God's name would you chop our full rotation into 360 parts? That seems bizarre. You might have thought when the metric system was being set up, there would be a push to define 1 metric degree, or whatever you would call it, as 1/100th, or maybe even 1,000th of a full rotation. There was a proposal to introduce something called a gradian, and you can still find these things on your calculator. Most calculators will have a degree mode, a radian mode, and a gradian mode, though I still have never heard of anyone actually using gradians. But what a gradian is kind of what I was describing before. Namely, 1 gradian is defined as 1/100th of a right angle. Again, a right angle being a fundamental mathematical idea. And some people might say, wait a second, isn't that a circular definition? Because don't we normally define a right angle as 90 degrees? Or in this case, a right angle would be 100 gradians. No, you don't actually need an angle measurement to define a right angle. You can just say, if we have a line and then another line cuts across it in such a way that 2 adjacent angles are equal to one another, then we define those angles to be right angles. That, in fact, is more or less how Euclid does it in the Elements. Euclid never mentions degrees or radians or anything like that anywhere. In fact, the unit of measurement for angles that Euclid sometimes refers to is the right angle. And so he would say that the sum of the angles in a triangle are 2 right angles. They add up to 2 right angles. And that would be one intrinsic way of measuring angles that goes all the way back 2,300 years. But I digress. Let me return to what I was saying about gradians. So if we defined a gradient to be 1/100th of a right angle, then each right angle would be 100 gradians, nice power of 10, and a full rotation would be 400 gradians. Such is a gradient. Once again, like the definition of a degree, it refers to something fundamental to mathematics, but something else that is arbitrary, that 1/100th. And even though having an angle measure that is defined as 1/100th of a right angle might seem in some ways more appealing to human beings with our 10 fingers than an angle measure that is 1/90th of a right angle, it really is equally arbitrary from the point of view of mathematics itself. What's so special about 100? What's so special about 90 or 360? There really isn't anything special about it. Historically, there are some interesting facts. Like this 360 comes from ancient mathematics, from ancient Mesopotamia, where the astronomers chopped things up into 60s and 360s because the ancient Mesopotamians used a base 60 system, not a base 10 system. But anyway, we could tell these stories all day, and they're very interesting. But the point is to get to a mathematically intrinsic notion of angle measurement, the kind of thing that could be understood by an alien intelligence without the aliens having to say, well, that aspect of it is just a reflection of human beings' evolutionary history or the particular culture of the people who came up with this particular way of measuring angles. No, we want something that is deeply, intrinsically mathematical, that the aliens would understand on its face. So it certainly makes sense to base it on a notion like a right angle, or a full rotation, of course, is 4 right angles, or a circle, something that is part of mathematics itself. And that is precisely what we're going to do. The aliens wouldn't understand why 10 was a special number to us, but they would certainly understand, for example, why the number pi was important to us. Naturally, they'd use a different symbol for it and a different name, but there's nothing peculiarly human about pi. Pi is serious mathematics. Why is pi built into the fabric of mathematics? Because, well, remind yourself what pi is. Pi is the ratio of the circumference to the diameter in any circle. And how do we know that in the great variety of circles, how do we know that the circumference to the diameter, that ratio, is the same on all circles? Does this definition even make sense? Of course it makes sense. As we discussed long ago, it makes sense because all circles, unlike all triangles, all circles are similar, which means that if we take the corresponding ratio of 2 lengths on any circle, they will necessarily be the same. So yes, circumference to diameter is the same in any circle whatsoever. And the value of that ratio we call pi. This is why the aliens will understand why pi appears frequently in our writings about mathematics, or writings in which we use mathematics, but the presence of all those powers of 10, say in scientific writing, won't mean anything to them. And thus, for the aliens, just like for us, the question of what is the numerical value of pi is a meaningful question, because it simply means how many times does the diameter fit into the circumference in any circle. Like if I have my circle here and I look at its diameter, I could lay it off along the circumference once, twice, 3 times, and a little bit more. And then the mathematicians, whether they are human mathematicians on Earth or alien mathematicians in some other galaxy, can try to figure out what that little bit is. And that would lead them to the notion of an irrational number, and so on and so forth. Eventually, they too would discover that pi is about 3.1415926535889, etc., except they would express it differently, because this is using base 10, and base 10 doesn't mean anything to them, presumably. But enough about alien civilizations. Let's get back to our own. I brought this definition of pi up here, not merely as a way of reviewing something important, but because it is going to lead us to our understanding of what a radian is. So I guess I will leave this stuff on the screen for a minute while I come over here and write down our definition of a radian, which is the following. If we lay a circle's radius along its circumference, nothing arbitrary here so far. This is all fundamental mathematics. We've got a circle, a radius, and now we are imagining taking that radius, laying it down along the circumference. So no weird 360s or hundreds or anything like that yet. But let's get back to our definition. If we lay a circle's radius along its circumference, the angle that it cuts off at the circle's center, what does that mean? Well, here's the circle's center. Here's that radius that we laid off on the circle. The angle that it cuts off at the center is this angle right here. So the angle that that radius cuts off at the circle's center is 1 radian. So that angle we're looking at right there is a single radian. And for each radius that I can lay along the circumference, I pick up another radian of angle measure. So this angle is 1 radian, but if I lay off another radius, it's going to cut off another radian. So this angle right here would be 2 radians. And notice what a large unit a radian is. Compared to a degree, which is a tiny little thing, a radian has some real heft. Anyway, there's our 2 radian angle. If we wanted an angle that measured 3 radians, well, of course, you know what we would do. So a natural question is, how many radians are in a full rotation? We'll come back to this picture I had over here. This is why I preserved it. How many diameters can I lay off on the circumference of a circle? Well, the diameter goes into the circumference exactly pi times. So how many radii can I lay onto the surface? Well, for each diameter, there are, of course, 2 radii. So if I can fit the diameter into the circumference pi times, I can fit the radius into the circumference 2 pi times. Each one of them cuts off a radian of angle measure. So how many radians are in a full rotation? The answer is 2 pi radians in a full rotation. It's a bit more than 6 1/4. Let me clean this up a bit. Okay, that's looking better. There's our definition, our picture of a radian, and this fundamental fact that there are 2 pi radians in a full rotation. First, notice that there is nothing in this definition that is arbitrary. No hundreds or 360s or anything weird like that. So the aliens would understand this one with no problem. This is an intrinsic definition of angle measure. And because it is intrinsic to geometry itself and doesn't depend on what base such and such culture used at such and such point in history, we might expect that it will make certain formulas simpler if we use this as our way of measuring angles rather than degrees or gradients or any other such things. And that's true. We'll see an example or two of that later. But first I just want to get used to the idea of measuring angles in radians, because it is admittedly weird the first time you meet it. But I promise you will get used to it. Everybody does. And if you move on in mathematics, into calculus, you will be using radians all the time, and it will become second nature. But of course, we want to be able to communicate in both radians and degrees, so we need to work for a little bit on doing simple conversions. This is easy. Everything comes from this fact. In fact, I'm going to reformulate this in a way that I think is even a little cleaner. If there are 2 pi radians in a full rotation, then how many radians are there in a half turn? Well, obviously, that would be half as many radians. So not 2 pi, but pi. That means that pi radians is the same thing as 180 degrees. And that is a fact you should bear in mind. You'll use it every time you think about radians from now on. So let's put this in its own special little box, in its own special place. This is the fundamental relationship that will allow us to convert back and forth between radians and degrees whenever we need to. So know it well and understand why it is so. Let's do some quick examples of conversions. Let's start with some of our special angles, those angles at which we could get exact values for our trig functions, like say 30 degrees. If I wanted to convert 30 degrees into radians, what would that be? Well, that's going to come straight from this relationship. 30 degrees is, of course, a sixth of 180 degrees, but that's pi radians, so it's going to be a sixth of pi radians. 30 degrees is pi over 6 radians. So just as before, we were often thinking about 30 degrees and multiples of 30 degrees. When we're using radians, we'll often be thinking about pi over 6 and multiples of pi over 6, like 60 degrees. What is 60 degrees in terms of radians? Well, we can already see two ways to think about that. First, let's just go back to our basic fundamental relationship here. 60 degrees, that's a third of 180, which is pi, so 60 degrees must be a third of pi over 3 radians. Or we could have thought 60 degrees, that's double 30 degrees. So how many radians? It's going to be double pi over 6, 2 pi over 6, which is pi over 3. Let's move up to 90 degrees. What's that going to be? Well, 90 is half of 180, but 180 is pi radians, so this is going to be half of pi. 90 degrees is pi over 2 radians. And very soon, whenever you see a right angle, just as right now you see that and you automatically think, 90 degrees, you should see that and think simultaneously, pi over 2 radians. Right angles are so fundamental that you'll see pi over 2's pretty much everywhere. A right triangle is a triangle that has an angle of pi over 2 radians in it. What about 45 degrees, our other basic special angle? How many radians will that be? Well, look, 45 degrees is half of a right angle, and a right angle is pi over 2. So that means 45 degrees is half of that, which is pi over 4 radians. And of course, we could build up other angles from these. For example, 135 degrees. 135 degrees, well, you are probably used to now the idea of thinking about 135 degrees like this. It's a right angle and then a 45 degree angle, or if you like, it's 3 45 degree angles. And since each 45 degree angle is pi over 4 radians, this is going to be 3 pi over 4 radians. And as long as we are dealing with our special angles and multiples of them, well, we can just think about it in this casual way. But what if I have something that is very far from special? Like if I have a 212 degree angle, and I want to know what is that in radians. Well, I will just do a conversion like you would do in a science class, say, when you're converting from inches to centimeters. When you're doing a unit conversion, you're always just using the old multiply by 1 trick. You're multiplying by 1, so you're not changing the value of something, you're just changing the form in a clever way. And what we would do here is I would say, well, 212 degrees. I'm trying to change the units from degrees to radians. I'm going to take my 212 degrees and very cleverly multiply by 1. But the 1 has to appear in a special form. The form is going to be such that the degrees will cancel with degrees, so I'll have degrees downstairs here, and I'll be left with radians up top. So now I just need to write down a fraction where I have radians upstairs and degrees downstairs, and the ratio is 1. So I will use my basic relationship here. Pi radians is 180 degrees. So the fraction that will be my 1 here, I want radians upstairs, so I'll put pi radians upstairs and 180 degrees downstairs. That way I'm just multiplying by 1 because pi radians is 180 degrees, so I'm not changing anything, so this equal sign really holds. The 2 degrees signs will cancel out and I'll just be left with radians. And when I do that, what happens? The degrees are gone and I get 212 over 180, which I guess reduces a little bit. Let's see, to 106 over 90, 53 over 45, but I still have the pi, of course. So 53 45ths of pi radians. And we are done. We have made our conversion. And of course, we could convert any number of degrees into radians by using that same conversion factor, piece of cake. Now please, don't memorize, as I've seen students do, To convert from degrees to radians, multiply by pi over 180. Just know this basic relationship, that pi radians is 180 degrees. If you know that, then the conversion is almost obvious. I promise you, I don't know off the top of my head. To convert from degrees to radians, multiply by pi over 180. I don't. I know it's either pi over 180 or 180 over pi, but I have to stop for a second and think about the units. But it takes literally all of a second or two. Memorize as little as you can. Understand as much as you can. Anyway, the same thing works in reverse. If I have something in radians, like say 1.2 radians, and I want to convert it into degrees, what do? I don't reach for some memorized conversion factor. I just think, well, look, like any conversion between any two units, whether it has to do with angles or lengths or areas or whatever, I just have to multiply by 1 in the appropriate way. Well, what do I have to multiply by here? The thing is given to me in terms of radians. I want it to be in degrees, so I need radians to cancel out. So I need radians downstairs and degrees upstairs. Now I just need to know some number of degrees that's equal to some number of radians. Well, everybody knows 180 degrees is pi radians. When I do the multiplication, the radians cancel out, and what I'm left with will be just in degrees. In this case, it will be 216 over pi degrees. Similarly, 4 pi over 7 radians. How many degrees is that? Well, I have to start with my 4 pi over 7 radians and multiply by 1 in the right way. I want the radians to cancel out, so I'm going to have pi radians downstairs, and I want degrees to survive, so 180 degrees upstairs. I'm just multiplying by 1. So of course this equal sign holds, because multiplying by 1 doesn't change anything. Or rather, it doesn't change the value of what I'm working with. It can change the form, and that's what I want, because I'm changing from something in radians to something in degrees. Anyway, when I multiply that out, the radians cancel out. I'm going to be left with just something in terms of degrees. In particular, let's see. Oh, well, the pi's cancel out as well, and I will be left with, I guess that is going to be 720 over 7 degrees. That's the exact number of degrees. If you want a decimal approximation, my calculator tells me that is about 102.9 degrees, which makes intuitive sense. This is a bit more than a right angle, and we know a right angle is pi over 2, half of pi. Well, 4/7 is close to 4/8, which is half pi, but it's a bit bigger than 4/8, because each seventh is bigger than an eighth. You'd rather have a seventh of a pi, PIE, than an eighth, because you get more of it. Okay, so that's all there is to say about converting between radians and degrees. It's just the old multiply by 1 trick, and of course, special angles, you will get used to values like 30 degrees is pi over 6, 60 degrees is pi over 3, 90 degrees is pi over 2, and 45 degrees is pi over 4. And you'll know those like the back of your hand before you know it. All right, enough about conversions. I mentioned that using radians will simplify some formulas. The big payoffs come in calculus, but I can still show you a very simple geometric example of that happening right now. Suppose we have a circle of radius r, and we wish to cut out a slice of pi, as it were. So our pi slice, or if you want a clinical term, our circular sector, has 2 radii as edges, and then a part of the circumference as its third edge. And let's call the angle between those 2 radii theta. Now, assuming we know r and theta, it should be pretty obvious that the length of that arc, the arc length of the crust of the slice of pi, if you like, that length is determined by r and theta, right? R tells us how large the entire pi is, and theta tells us what percentage of the pi we are getting when we take our slice. So let's give that arc length a name. It's traditional to call it S. I have no idea why. We could just as easily call it L for length. In fact, let's defy tradition. L it is. Now, since L, that arc length, is clearly determined by r and theta, we should be able to write down a recipe. L is equal to something involving r and theta. Let's figure out what that formula would be. And as we will see, it will depend upon our units with which we measure theta. So let's do it. This is nice and easy. We really only have to make one observation, which is that L takes up a certain proportion of the entire circumference, and theta takes up that exact same proportion of the full rotation angle, right? I mean, if theta takes up half of a full rotation, then obviously L, the arc length, takes up half of the full circumference. So there's nothing mysterious about this. If L takes up 39% of the circumference, then theta takes up 39% of the full angle. You get the point. To come up with a formula for L in terms of r and theta, all we have to do is translate that basic intuition into algebraic symbols. L is to C, arc length to full circumference, as theta is to a full rotation. However we might measure that. Okay, so far so easy. Now we just want to take that and solve for L, which gives us L is C times theta over a full rotation, however that's measured. Oh, and of course we know that the circumference is 2 pi r, so now we have that the length is 2 pi r theta over a full rotation. So, if theta is measured in degrees, we get L is 2 pi r theta over a full rotation, which in degrees is 360. We can simplify a little bit by canceling a 2 from top and bottom, but that's it. Here is our recipe for that arc length, pi r theta over 180. Okay, but if theta is measured in radians, then our general recipe collapses into something nicer. We're going to get 2 pi r theta upstairs, but our full rotation, which goes downstairs, if we're measuring in radians, is not 360, it's 2 pi, which is much nicer because, like magic, that 2 pi cancels with this 2 pi, leaving us with plain old r theta, which I hope you will agree is a much nicer recipe and much more memorable than this version in degrees. The degree version has the r theta embedded in it, but it also has this nasty pi over 180 clinging to it like a barnacle. And that, in fact, is the typical pattern we see, where you get a nice formula in radians, but if you express it in degrees, you get some ugly factor like pi over 180. By switching over to radians, you get rid of all that detritus. As I say, you will see the biggest payoff in calculus when you learn about the derivatives and antiderivatives of the trigonometric functions. There, too, everything is very clean when you work in radians, which we do, and unnecessarily ugly if you do everything in terms of degrees. Okay, so that is actually a formula worth knowing, that when we have a pie slice taken from a circle with radius r and angle theta, then the arc length of that slice, its crust, is simply going to be r theta with one important caveat, provided that theta is measured in radians. In the exercises in the book, you will find a similar formula for the area of a pie slice. It's not quite as simple as that one, but it works out pretty cleanly if you do everything in radians, and is much more ugly if you do it in degrees, or even in gradians, God help you. I still would like to know who, if anybody, uses gradians. Why is it on your calculator? Somebody must be interested in it. I feel like I need to speak to somebody in the gradient lobby and find out what this is all about. But you can come up with that area formula on your own. What I want to do now is give you some examples of evaluating the trig functions at special angles when those angles are expressed in radians, which they usually will be. And really, there's nothing new here, because if you know how to do it in degrees, you can always convert over to degrees and do it that way, or at least in your mind you can do it that way. But you'll see it so frequently in radians that it helps to do lots of specific examples so that you can begin to think somewhat directly in terms of radians. Oh, and actually, before we get started with specific examples, I should mention something. Radians are so ubiquitous in any mathematics beyond where you are right now that the default assumption is that you are using radian measure. In other words, if no units are mentioned on an angle, the default assumption is that radians are meant. So if you see something like sine of 2 with no units on the input, that means sine of 2 radians, which is very, very, very different than sine of 2 degrees. Sine of 2 radians would be the sine of a big fat obtuse angle like this. So it would be the y-coordinate of that point. This is not at all equal to sine of 2 degrees. 2 degrees is a tiny angle. It would be the y-coordinate of that point. Obviously, that point and that point have very different y-coordinates. So totally different. Units matter. And when no units are expressed, radians are assumed. If you're going to use degrees, you have to include that degree symbol. And in fact, no one ever writes radians on the inside of a trig function. It's just presumed. In the same way that when you write, the square root of 6, nobody puts a little 2 up there. It would look weird if you did it. It's just taken for granted that if there's no symbol there, what is meant is second root, the square root. So with that in mind, Let's look at some examples. Let's begin easy. How about sine of pi over 6? All right, well, you just have to think. Pi over 6, what's that? Well, pi is 180 degrees. It's the basic fact we all know. A sixth of that is 30 degrees. So this is the same thing as sine of 30 degrees. I don't have to write this out. I can, but I could just think that in my mind. Sine of pi over 6 is the same as sine of 30 degrees, and everybody knows that's half. Easy? Easy. All right, how about cosine of pi over 3? Pi over 3. Well, pi is 180 degrees, so pi over 3 is 60 degrees. That's cosine of 60 degrees. Let's just do this in our heads. But cosine of 60 degrees, we know, is sine of 30 degrees. Which again is a half. So we could just write down at once, that's a half. And you see how easy this is. Notice that even something like this, if you want to, especially at first, you could express this in more detail. You could actually write out cosine of pi over 3 is the same thing as cosine of 60 degrees, which is the same thing as sine of 30 degrees, which is a half. You can do it all in your head, or you could write it all out. Either way, you should be sure you understand why each one of these equal signs holds. This holds just by the definition of radians. Pi over 3 radians is 60 degrees. This holds by that cofunction identity. The cosine of an angle is the sine of that angle's complement, the thing you have to add to that angle to bring it up to 90 degrees. And this holds, of course, by basic geometry, those 30, 60, 90 triangles, which are half of an equilateral triangle, which gives us those usual ratios of 1 and 2 and square root of 3. Anyway, it's little things like that you want to review as you go, because those are the important properties of trigonometric functions. That's how you get to know trigonometry, by reminding yourself of all these different little relationships and where they come from. Even if, ultimately, you just see cosine pi over 3, and you quickly think your way through that 60 degrees, cosine of 60 is sine of 30, which is a half, and you just write down a half. Let's do another one. How about sine of minus pi? Well, there's a few ways we could do this. We could visualize it directly, or let's use a different property of sine. We know that sine is an odd function, as we recently talked about. So sine of minus something is minus sine of that something. The minus gets pulled through the sine. So that equal sign holds because sine is odd, an important property. Anyway, what's sine of pi? Well, think about the unit circle. If we rotate through pi, we end up right here. Sine is the y-coordinate. What's the y-coordinate of that point? Well, of course, it is 0. And when you negate 0, you still have 0. Now, I put that step in just so we could review the fact that sine was odd. But you could have looked at this and directly thought, well, minus pi. Pi is a half turn, but it's negative. That means we're going this way. But that brings me to the exact same point. Sine, of course, is the y-coordinate, so it's 0. And we could have seen that directly. Let's do another. Cotangent of pi over 6. Well, how do we deal with cotangent? Well, by definition of cotangent, that's 1 over the tangent of pi over 6. And what are we going to do with the tangent of pi over 6? Well, we just have to think. Pi over 6. Pi is 180 degrees, so pi over 6 is 30 degrees. What's the tangent of 30 degrees? Well, you probably know it's 1 over root 3. And if you don't know that off the top of your head, well, you draw that 30, 60, 90 triangle I mentioned a while back, and you read it off of that triangle. Either way, we end up with 1 over root 3, which of course is just plain old root 3. You see how easy this is? We'll do a few more just because you are guaranteed to have a page on a test where you just have to bash these kind of things out. So let's do sine of 3 pi over 4. What's that? Well, think about it on the unit circle. Pi over 4. Well, pi over 2 is a right angle, everybody knows. Pi over 4 is half of that, so that's our 45 degree angle. We've got 3 pi over 4s, so that takes us 1, 2 over here. There's our 3 pi over 4. We are looking for the y-coordinate of that point. Well, we know how this works. We just think about the reference angle, and then we end up looking at the y-coordinate of the corresponding point in the first quadrant. But what is that angle? What is that reference angle right here? Well, of course, it is pi over 4, because a half turn is pi, and we've got 3/4 of the way already. So this is a quarter of pi. These 2 points obviously have the same y-coordinate, so sine of 3 pi over 4 is the same thing as sine of pi over 4. Pi over 4 is 45 degrees, and everybody knows sine of 45 degrees is 1 over root 2, or if you like, root 2 over 2. So really just a matter of thinking about the unit circle in the usual way, and understanding how radians relate to degrees, which is pretty easy. Okay, maybe one or two last really disgusting ones, just to show you that no matter how nasty I make it, it's still really straightforward, and you can just think your way through it. How about cosecant of minus 5 pi over 3? Honestly, figuring this out and being able to justify each step along the way is a pretty good test as to whether someone really understands trigonometry or not. So let's see if we do. Okay. First of all, we're dealing with cosecant. Nobody likes cosecant, so let's rewrite this in terms of a friendlier trig function. Cosecant, by definition, is what? 1 over sine of minus 5 pi over 3. Okay, well, at least we got rid of the cosecant. Ugh, but we've still got this negative in there. Hey, wait a second. We dealt with something like that just a few minutes ago. Sine is an odd function. That means this negative can be brought outside, which means that this turns into 1 over minus sine of 5 pi over 3. Now I'm already feeling much more comfortable, because now I just have to deal with sine of something positive as opposed to cosecant of something negative. Okay, but still I'm dealing with 5 pi over 3. I have to think, 5 pi over 3. Where does that live on the unit circle? Well, there's different ways you could think about it. The thing that occurs to me is that 6 pi over 3 is 2 pi. That would be a full rotation. But we only have 5 pi over 3. That means I'm pi over 3 short of a full rotation. And pi over 3, well, that's a third of 180 degrees. That means I'm short by 60 degrees. So something like that, where my reference angle is 60 degrees, or pi over 3, however you want to see it. That's not the only way you could have identified where the point was. You could have thought, well, pi over 3 is 60 degrees. I'm taking 5 of them. 5 times 60 is 300. 300 leaves me 60 degrees short of a full rotation. That's fine too. Either way, you get to the same point. And we are looking for the sine. So we're looking for the y coordinate of that point. It's definitely going to be negative, but it's down here in the fourth quadrant. So let's refer it back up to the first quadrant. We want the sine, the y coordinate. Well, obviously, those 2 points have y coordinates that are equal but opposite. One is positive, one is negative, but they have the same magnitude. So I could say that in place of sine of 5 pi over 3, which is the y coordinate at that point, I could put the negative of the sine of 60 degrees. So that'll be something like that. Well, that's nice. These two negatives cancel out, and then I'm left with sine of 60 downstairs. Sine of 60, that's one of the ones everybody knows off the top of your head, is root 3 over 2. So that all comes out to 2 over root 3. Or if you want to rationalize your denominators, 2 root 3 over 3. Either way. And we've got it. So again, not too bad, all things considered, even though this looks disgusting. Just be sure you understand why each one of these equal signs holds, and you're in good shape. All right, one last. Secant of negative 7 pi over 6. What's that? Well, let's get rid of the secant. By definition of secant, that's 1 over cosine of that ugly angle, minus 7 pi over 6. Ooh, how am I going to deal with that? Hey, I've got cosine of minus something. What do I know about cosine? I know that cosine is an even function. That means it absorbs that negative. So all this stuff is going to be equal to 1 over cosine of 7 pi over 6 without the negative. All right, cosine of 7 pi over 6. That doesn't seem too bad. Let's just visualize it on the unit circle. Where does it live? Well, let's see. 7 pi over 6. 6 pi over 6 is pi. And of course, pi is a half turn. So 6 pi over 6 would just take me here. But I've got an extra pi over 6. I've got 7 of them, not 6. Each pi over 6 is 30 degrees, 1/6 of 180. So that means I've got my half turn and then another 30 degrees, another pi over 6. So maybe something like that. And my reference angle is pi over 6, or 30 degrees if you want to think about it that way. We are looking for cosine, so the x coordinate at that point. How are we going to find it? Well, let's refer it to the first quadrant. Despite my awful drawing, you get the point. The x coordinate of this point and the x coordinate of this point are going to be equal but opposite. Same magnitude, opposite sign. And of course, the x coordinate of this point is the cosine of 30 degrees. So we can say this stuff is not the cosine of 30 degrees, but the negative of the cosine of 30 degrees. And what's the cosine of 30? Well, we can do that in our head. By that cofunction identity, the cosine of 30 is the sine of 60. And everybody knows that the sine of 60 is root 3 over 2. So that gives us minus 2 over root 3. Or if you like, minus 2 root 3 over 3. and we are done. And that's about it. If you can do those, I think you can pretty much do them all. Well, I don't know. What about this? What about the tan of 913 pi? Can we do that? Sure we can. And it's a lot easier than this one, which is why I stuffed it in the corner here. 913 pi, what's that? Well, look, pi is a half turn. Every 2 half turns you make, every 2 pi is a full rotation. So 2 pi gets you back here, 4 pi gets you back here, 6 pi gets you back here, 912 pi gets you back here, which means 913 pi brings you right here. What's the tangent of 913 pi? Well, what's the slope of that radius? That's what the tangent measures. It's a horizontal line, so its slope is 0, which means the tangent of 913 pi is 0. Okay, now I really am done with that stuff. I've said about all there is to say about radians, but I do have this little and graphs here as well. So I would like to say a few words about graphs, which will be the major theme of the next lecture. What I want to do here is mostly just connecting things we've already talked about relating to the graphs of the trig functions and connecting those to radians. Actually, there's a little bridge I could take from the previous topic to this one. I mentioned that when we write something like sine of whatever, the default assumption is that we are working with radians. If we want to specify degrees specifically, we have to put a degree sign in there. Well, something similar happens when we're talking about graphs of trig functions. If we are interested in the function f of theta is sine theta, and we want to graph that function, the default assumption is that theta is measured in radians. So if we put theta on the horizontal axis and y equals sine theta on the vertical axis, well, what happens? When theta is 0, well, we have sine of 0, the y-coordinate at that point, which is obviously 0. That means our graph begins at 0. Then as theta increases from 0 all the way, let's go to pi, so all the way to a half turn, the sine of that moving point, the y-coordinate, goes first up to 1 and then back down to 0. It reaches 1 at the angle pi over 2 and gets back down to 0 at the angle pi. So the graph will look like this. As theta goes from 0 to pi over 2, the sine rises from 0 to 1. As theta goes from pi over 2 to pi, the sine falls from 1 back to 0. And then the same thing happens on the other side, except now theta is going from pi to first 3 pi over 2, where the sine is minus 1, then all the way up to 2 pi, where the sine is back to 0. So on the graph, that looks like this. And that's the basic cycle that we see repeated over and over and over and over as the point goes around. So this, we would say, is one period of the sine wave of this periodic function. So I will just put in an extra period here. Think about what happens. Each period is 2 pi long. So that means this is going to occur at 4 pi. This point right here is going to be 3 pi. And you could fill in the other pieces as needed. Halfway between 2 and 3 is 2.5. So 5 pi over 2. Halfway between 3 and 4 is 3.5. So 7 pi over 2. And same thing on the other side. So nothing new here except the labels on the horizontal axis. But since sine repeats itself every 2 pi, we say that the period of sine is 2 pi. Start at any point and take its sine and then add on one full period. In other words, add on 2 pi, take the sine again, and you get the exact same value. We could even translate that into a kind of identity where we would say sine of anything plus 2 pi is going to be the same as sine of pi. This is actually more obvious on the unit circle itself, because whatever angle theta we rotate through, the sine of pi is the y-coordinate there. That's what that means. Sine of theta plus 2 pi would be that, plus another full rotation, so the y-coordinate there once again. So obviously they're going to be the same. Okay, so I think you know the basic shape of the sine curve. It crosses through the axis every pi, 2 pi, 3 pi, 4 pi, minus 2 pi, so on and so forth, with crests and troughs in between. What about graphing the cosine function? What would that look like? Well, think about the unit circle. Where does the graph begin? When theta is 0, what's the cosine? Well, that's the x-coordinate of that point, which is obviously 1. So the graph of cosine begins not at 0, but at 1. And this is really the key distinction, because apart from that, everything is going to look quite similar. We're still going to get the basic wave, we're just starting in a different place. As we increase theta from 0, going up to pi over 2, what happens to cosine? What happens to the x-coordinate at that point? Well, it begins to retract from 1 to something smaller, something smaller, something smaller, and finally the x-coordinate becomes 0, which means that on the graph, we would see something like this. And then, of course, as theta goes from pi over 2 to pi, completing that first half turn, what happens to the cosine, the x-coordinate at that point? Well, it started at 0. Now it starts to become negative. It gets more and more negative, hitting a value of -1 when theta is at pi. So our graph would continue on like so. And you know how it goes. As we go from pi all the way to 2 pi, what's going to happen to cosine? The x-coordinate at that point, it starts at -1. It's going to start creeping up past 0 and all the way to 1, which on the graph will look like this. And now we've got it. We've got one full period of the cosine function. We've gone around the horn. And if we go around again, of course, we just repeat this like so. And that takes another 2 pi. So that means right here we would be at 4 pi, and this would be 3 pi, and my graph's not very good. That should be halfway between 2 and 3 pi. Well, that's 2.5, so 5 pi over 2. This would be halfway between 3 and 4 pi. 3.5 is 7 pi over 2, and we would see the same thing on the other side, and this wave would continue on and on forever, bobbling between -1 and 1. It looks exactly like the sine wave. It's just been shifted over a little bit so that instead of beginning at 0 and climbing up, it begins at 1 and begins climbing down. So cosine also has a period of 2 pi. It repeats itself every 2 pi. That's the basic cycle. This is in contrast to the tangent function, which unlike sine and cosine has a period of merely pi. Let's remind ourselves of what it looks like. Okay, what's the tangent of 0? Well, tangent gives me the slope of the radius. The slope there is 0, so tangent begins at 0. And then as theta goes from 0 to pi over 2, what happens to the radius's slope? It increases. It hits 1 at pi over 4, and then it really starts going through the roof. And the slope approaches infinity. And at pi over 2, it's not even defined. So on the graph, that would end up looking like this, where we have that asymptote at pi over 2. And we see exactly why, because there is no slope there. And as we approach it, the slope goes to infinity. If we shoot beyond it, between pi over 2 going down to pi, well, now we have an extremely negative slope, and now a slightly less negative slope, and a less negative slope, and now maybe a slope of -1, and the slope is still negative, but approaching 0 from below, until finally at pi, the slope is 0 again. So on our graph, we have all those negative slopes down here, and the picture would look like that. And you remember how this works. If we go past pi, towards 3 pi over 2, what happens to the slope? It starts at 0, then it becomes slightly positive, then more positive, and it gets very, very positive. Slopes going to infinity until it's not even defined, which is another way of saying an infinite slope at 3 pi over 2. So we would have something like this. And then, of course, as we go from 3 pi over 2 to 2 pi, we see slopes increasing from -infinity to -1 and all the way up to 0 when we hit 2 pi. So on the graph, that would look like this. And if we continued to the right and to the left, of course, the pattern would keep going on like so. At all multiples of pi, the value of the function is 0, and at pi over 2 and 3 pi over 2 and 5 pi over 2 and so on and so forth, we get these asymptotes. So one basic period of the tangent function might look like this. And the period of tangent is not 2 pi, but pi. That's the smallest value at which you can take any point, see what tangent does to it, push it along by another pi, see what tangent does to it there, and you're going to get the exact same thing out. What we have is that tangent of anything plus pi is the same thing as tangent of that anything. Tangent just repeats itself every pi. It's probably easier to see on the unit circle itself. Take any angle theta, the tangent is the slope of that radius. That would be the tangent of theta. But what would the tangent of theta plus pi be? Well, I'd have to add on another pi, another half turn, and it would be the slope of that radius. Well, the two radii lie on the same line, so of course they have the same slope. It's the slope of that line. So of course those tangents are equal. All right, But what about the graphs of secant and cosecant and cotangent? I hear you cry. Well, all three are easy to figure out using the fact that they are reciprocals of functions whose graphs we already know. You'll explore those in an exercise in the book, so I will leave that to you. But I will say the graphs that are most important are the ones we've looked at, particularly the sine function, since that is what we use to model periodic behavior of all sorts, and that is what we will talk about in the next lecture. So until then, goodbye.